With the landing of a probe on Comet 67P, the European Space Agency has achieved the most complex space mission of the century, but it has not all been according to plan. The early days of rocket technology were littered with spectacular failures. Cold War adversaries, the Soviet Union and the United States, were in a rush to acquire missile technology to deliver the newly developed hydrogen bomb. During the Second World War, Germany had been working on ballistic rockets. Many of their early attempts had also been unsuccessful. By October 1942, the German team, led by Wernher von Braun, had a workable prototype. When the weapons went into mass production, V-2 attacks were launched against Britain and Belgium. With the fall of Berlin, Russia and America were keen to get their hands on V-2 technology, and German technicians captured at the end of the war were vital to the early rocket programs of both sides. In the 1950s, the Soviet Union began work with clustered engines, and the R-7, the forerunner of today's Soyuz, emerged. The new R-7 featured two central stages flanked by 4 boosters, a configuration that's still used today. It could deliver a heavy thermonuclear warhead to a target in North America. And the R-7 was powerful enough to put a satellite into orbit. On October 4th, 1957, the Soviet Union launched an 83-kilogram satellite called Sputnik, and everything changed. As it orbited, Sputnik transmitted a beep that could be picked up by radio as it passed overhead. America took this as a direct challenge. The US had 2 candidates close to launching a satellite: an Army team with its Jupiter C missile, headed by German V-2 engineer Wernher von Braun, and a naval team called Vanguard. Compared to the Army's Jupiter 1, Vanguard was largely unproven. But because the US was reluctant to rely upon von Braun and his German team, Vanguard was given the task of launching America's first satellite. However, the Russians had a new surprise. 1 month before Vanguard's launch date, and barely a month after Sputnik's flight, another R-7 was on the pad. This was the launch of Sputnik 2. And this time there was a passenger, a terrier called Laika. In the US, Cold War paranoia was becoming extreme.
It gets the American people alarmed that a foreign country, especially an enemy country, can do this, and we fear this.
Pressure was building on the Vanguard team to salvage American pride. In addition to the reporters and photographers covering the event, it was announced that the launch from Cape Canaveral would be screened live. It was a national humiliation.
And here, Pickering, Van Allen, von Braun.
Von Braun's team was given the go-ahead. In weeks, the group developed a satellite named Explorer 1 that was a fraction the size of Sputnik.
Jupiter C.
Unlike Sputnik, which just carried a radio transmitter, Explorer 1 contained a scientific payload.
News of the day has shown you
The Juno 1 was a modified Redstone rocket, with a rotating upper stage, a simple technique devised by von Braun for doing away with a final stage guidance system.
The four-stage Jupiter C in the tense period before time zero at 10:48 p.m. The last three stages are set spinning on takeoff for guidance purposes.
It was simple, but it meant that Juno could not deliver its payload accurately to a circular orbit. But the Americans were in a hurry.
In 1958, free men everywhere lifted their gaze to Freedom's satellite.
Later in 1958, President Eisenhower established a civilian-led space agency which absorbed much of the Army missile unit as well as the Vanguard program. It would be known as NASA. In 1959, NASA selected 7 astronauts for a manned space program which only existed on paper. Russia also had selected a cosmonaut corps and was working to put the first man into orbit. The research, backed by huge engineering budgets, was becoming a proxy war between the superpowers, and so far the Soviet Union was winning. But NASA had inherited the X-15 program, a rocket-powered aircraft that was delivering valuable data about flight control at the boundaries of the atmosphere. The X-15 glided back to the ground without power, and the techniques gathered here were of benefit to NASA when the space shuttle was in development. One of the X-15's pilots would join NASA in its second intake of astronauts. His name was Neil Armstrong. But the Soviets were forging ahead. After several mishaps, they had returned a pair of dogs, Belka and Strelka, safely from space. And in 1961, they were preparing to put a man in orbit. On the 12th of April 1961, a young Air Force pilot climbed into his Vostok 1 capsule. His name was Yuri Gagarin. The first man in space. The Soviet Union had set the most prestigious record yet. The United States had a spacecraft, the Mercury capsule, but they needed a heavier booster to take it to orbit. Explorer 1 had been lifted by a Redstone derivative, and early unmanned Mercury flights would also use the Redstone. Alan Shepard was due to make America's first manned spaceflight atop a Redstone, but it would be a suborbital flight. The new, more powerful Atlas would take the first astronaut into orbit, and so far, neither launcher was performing reliably. Finally, in May 1961, after a chimpanzee had tested the Mercury-Redstone combination, Alan Shepard would become the first American to fly in space. The flight lasted 15 minutes. Shepard and his Freedom 7 capsule were picked up 480 kilometres off the coast of Florida. Later that month, America's newly elected President Kennedy committed his country to a landing on the moon.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
It was the beginning of the space race, the most concerted scientific effort in history. No other instrument has made as big a contribution to humanity's knowledge as the Hubble Space Telescope. Yet the regular maintenance it needs is no longer carried out, and its days are numbered. Since the 18th century, when William Herschel discovered Uranus, telescopes have been getting bigger. Increases in size allowed us to see more distant objects. But it was not until Edwin Hubble that we learned just how distant some of these objects were. It had been thought that our galaxy was the universe until 1924, when Hubble proved that we were just one of countless galaxies in the universe. But astronomers were reaching the technical limit of their instruments, not because of their size, but because of distortion from the Earth's atmosphere. In 1946, astronomer Lyman Spitzer proposed an orbiting telescope above the distorting veil of the atmosphere. It was a wild idea, years ahead of humanity's technical capability, but it was built, and the space telescope named after Edwin Hubble has been in orbit since 1990. No single instrument has contributed more to our understanding of the universe than the Hubble Space Telescope. But it hasn't been straightforward. Something as complex as an autonomous telescope located in the harsh environment of space needs regular maintenance, and it was only possible because of the Space Shuttle and its ability to serve as a work platform. Without the Space Shuttle and its regular servicing missions, Hubble's initial design inadequacy and a series of component failures would have left it as a very expensive piece of space junk. After Discovery's deployment of the Space Telescope in 1990, there were 4 subsequent servicing flights. Hubble was both repaired and upgraded on these missions.
As the vehicle passes through the area of maximum dynamic pressure.
Atlantis, Houston, no action.
With the shuttle now withdrawn from service, there will be no more on-orbit maintenance. Components readied for Hubble's last servicing mission included new gyros, batteries, fine guidance sensor, astronaut tools, support hardware, a new docking ring, the carrier systems, and 2 new instruments. But building the hardware and packing it for flight to orbit was just a part of the preparation. At NASA's Neutral Buoyancy Laboratory in Houston, mock-ups of the shuttle's payload bay and the Hubble were available for the exhaustive training the astronauts needed. Conditions have to match those that the astronauts will experience on orbit. Problems encountered in the pool are solved before the team flies. In 2004, when a power supply blew, Hubble lost its imaging spectrograph. Repairing this component was something never envisaged by the telescope's designers, so special techniques and tools had to be developed. As the flight date approached, all the hardware was packed into special shipping containers for transfer to the launch site, where the next phase of the operation began. On March 2nd, 2004, an Ariane 5 blasted off from Kourou in French Guiana. It carried the Rosetta probe, one of the most ambitious deep space missions yet launched. Recently, it was brought out of a 3-year hibernation.
When I first heard the idea of Rosetta, I thought it would be extremely difficult.
We've never flown a spacecraft to a comet.
Its mission is to rendezvous with a comet, and it has had to travel a complex flight path to get there. Previous deep space probes have carried radioisotope power supplies, but Rosetta is designed with solar panels. It also carries a lander called Philae. The course Rosetta has followed has taken it past Mars and then back past Earth to gain assistance from the planet's gravitational fields. The probe skimmed past Mars at just 250 kilometres. Originally intended to meet comet Virtanen, launch delays meant a new comet had to be targeted. Rosetta reached a maximum distance from the Sun of 780 million kilometres, taking it beyond the orbit of Jupiter. During its cruise, Rosetta photographed asteroids, Steins and Lutetia. Starting last May, a series of thruster burns were monitored by members of the Rosetta mission team. The first of 3 major burns took place, with Rosetta 500 million kilometres away. It used 218 kilograms of fuel and lasted 7 hours and 16 minutes. It brought Rosetta into phase with its target, comet Churyumov-Gerasimenko. Over several months, 10 separate corrections were needed, and by August, the probe was roughly 100 kilometres from the comet. Soon, team members began seeing just what comet 67P Churyumov-Gerasimenko looked like. These pictures are a computer-generated recreation based on the first images of the comet. As it's still a long way from the Sun, no tail has yet developed.
It's only when you come closer to the Sun, this comet activity, this material starts to become active and it's outgassing, and then the cometary tail is formed, and this is what we normally see in the sky.
Because the comet's mass is so small, Rosetta will have to be at a very low relative speed to orbit it. At the moment, the probe is carrying out a series of triangular manoeuvres to track with the comet. Black and white images relayed by Rosetta's navigation cameras surprised scientists, who were expecting a much smoother object where traces of surface ice were apparent. Of 5 possible landing areas, landing site J was selected. For the Philae lander, it had the best combination of solar illumination and radio access to the Rosetta mothership.
The shape of the comet is definitely a bit unexpected. I consider it at the same time fantastic. It's a unique object. On the other side, has posed us some headaches in finding proper landing site because of this unusual shape.
The Philae lander was released from a distance of 20 kilometres. Its 4-hour drop was timed so that it would arrive at the intended area, taking into account the comet's 12-hour rotational period. Philae's 3 legs are tipped with small screws designed to anchor the craft on contact with the surface. On Earth, the lander weighs 100 kilograms, but although Comet 67P is the size of a mountain, its gravity is very slight. At the comet's surface, Philae has a weight equivalent to a piece of paper. This is a problem that leg screws and a small anchoring harpoon were designed to overcome. In addition, a small thruster at the top of the lander would push the craft down on contact with the surface. This is how it was supposed to happen, but scientists, who had to wait for a message relayed via Rosetta, were confused. It took an hour for a confirmation signal to reach mission control in Darmstadt, and initially there was celebration. But after hours of analysis, it became apparent that the anchoring devices had all failed, and the probe had bounced back up to a height of 1 kilometre. After initial contact within 1 metre of the intended landing ellipse, Philae finally came to rest at the base of a cliff. It was functioning well and sent back images of its surrounds, including this picture of its foot wedged up against the cliff. This was not a good place, as the craft's solar panels will receive only limited sunlight. While its batteries still had enough charge, the lander was asked to drill out a surface sample, analyse it and relay the results to the Rosetta mothercraft. This went smoothly, but Philae's batteries are now flat. It is hoped that as the comet approaches the Sun, the craft will receive enough light to recharge its power supply. Meanwhile, the Rosetta probe will continue to follow Comet 67P as it warms and develops its characteristic tail. A growing cloud of debris is orbiting the planet, threatening satellites. The high-velocity junk is jeopardizing the utility of near-Earth space. Since the earliest days of rocket launches, thousands of satellites have been delivered to Earth orbit. Today, an awareness of orbital debris means satellites at the end of their lives are set on a course that will see them burn up in the atmosphere. But many satellites remain aloft, and upper stages containing unburnt fuel will continue to drift, sometimes with alarming consequences. A cloud of orbital debris has been building up around our planet. This has serious implications for new satellite launches. ESA tracks the larger pieces of this orbital debris to see whether current satellites are in danger of collision. Ground stations are important in determining the orbital parameters of defunct satellites that can no longer communicate. Only 7% of monitored objects are functioning satellites.
Of the 16,000 to 17,000 objects that we can track from ground stations up there, just about 1,000 are operational spacecraft. All the rest are remnants of past spaceflight activities, and more than one-half of these objects are in fact fragments from on-orbit collisions recently, and also fragments from on-orbit explosions.
Satellites at the greatest risk are those in north-south orbits, like the Earth observation satellites. The tracks of these craft converge at the poles, and this is where the highest likelihood of collision exists. There have already been 4 major collisions in low Earth orbit. The most serious impact was the one between an Iridium satellite and a defunct Cosmos satellite in February 2009. They collided at a relative speed of around 42,000 kilometers per hour, creating an additional 2,000 pieces of debris. This debris cloud has continued to spread across different polar orbits. According to international space law, responsibility for any debris or abandoned satellite remains with the owner. Regulations require new satellites to carry enough fuel to enter a decaying orbit at the end of their usable life. Schemes to deorbit dangerous objects are being devised, but they are very expensive.